So what is the relationship between intermolecular forces and physical properties? Well, it goes like this. The stronger the intermolecular force, the more energy or heat is needed to overcome these intermolecular forces. So what you should be doing is you should be writing down these two statements. Um, uh, I want you to write them because, again, they're very, very important. So it takes a lot of energy, heat, to pull molecules apart, and that results in high boiling points. And it takes a little energy, heat, to pull molecules apart. That results in low boiling points. So that's the explanation here. Let's look at an example, and I'm going to show you a simulation here. If we have pentene, all it has is van der Waals. These are non-polar. This is a non-polar molecule, CH-CC bonds. It has a boiling point of 36. So again, this is relatively weak intermolecular force. So that's why you have a low boiling point, low BP. As you go to the next one, which is a dipole-dipole interaction, you have butanol, which is an aldehyde. The boiling point jumps to 76 degrees Celsius. Again, you need more heat to pull these molecules apart. And then finally, when you get to alcohol, which has hydrogen bonding, notice the OH, the boiling point jumps to 118 degrees Celsius. Look how high. This is a huge, huge difference. So again, it takes more energy. So this would be high. Before it's high, let's just write this down right here. Strong IMF. Which results in a high boiling point. So I wanted to show you this, although it applies to water, but that's the idea behind it. If you have those water molecules, notice the delta, the plus and the minus. I know they don't show them as delta, but these are your oxygens and these are your hydrogens, the white spheres. The delta plus is because hydrogen is less electronegative, delta minus because oxygen is more electronegative. Nevertheless, let's actually simulate, let's play them, and you'll see that these lines are the hydrogen bonds. So when it's at low temperature, this is low temperature, they're not moving as fast. Temperature gauge is here, or the thermometer. But we can actually increase the temperature. Once we increase the temperature, the reason why they start moving faster, you're introducing more kinetic energy. And again, the reason why you start breaking these hydrogen bonds, they're not as effective as they used to be. But again, it took a lot of energy. Look how much I pressed the heat here. In fact, this is why it has a high boiling point, is that intermolecular force hydrogen bonding is so strong. Very well. So let's go down here and look at the different alkenes here. If we compare different alkenes, so you're going to, before we compare the alkenes, you're going to go with hydrogen bonding as your strongest. Then you have your dipole the second, and then the weakest is your van der Waals, which are, again, they have the lowest boiling points. So if we compare alkenes, we say that the larger the alkene, the higher the boiling point will be. So let's look at an example. Here, the boiling point of This alkane, which is butane, is a negative 0.5 degrees Celsius. As we move here, notice that there's an extra carbon there. I'm sure you can see it. So this one has 4 carbons. And now this one has 5. So the boiling point of this is 36 degrees Celsius. And the reason why is because it has more surface area. So it's a longer molecule, so now you have increased surface area. Now, the moment we start with the branching, notice how you have a branch here. The boiling point dips to 27.9 degrees Celsius. And once again, the reason why you do this, why this happens, is because again, you have a smaller surface area now. I'm going to show you in the last one. And in the last one, the boiling point is really 9 degrees Celsius. Think about it. This looked kind of elongated like this. Here's another one. So you see that there's more surface area between the delta plus and the delta minus, so the interaction can take place in between. Whereas this one, if you were to draw this, they would kind of look like 2 spheres right here. And again, there's a less surface area interaction. Okay, so very small surface area. So that's why the branching here, we have 2 branches, resulted in a dip of the boiling point. So with more branching, less boiling point. So here, I'm going to summarize them for you. More branching, lower boiling points, longer alkanes, they have higher boiling points. So these are 2 trends you need to remember.